Hello there! Welcome back to Physics and Engineering. Let's learn some physics today. So today we are going to be talking a little bit about energy by looking through chapter 8 of your textbook. So you will need, number one, your physics notebook. We're going to open up and take some notes. And you will also need your physics textbook. So if you could please make sure you have both of those guys out. All right, in your physics textbook, we are going to open up to page 103, which is chapter 8, titled Energy. So I wanted to talk through just a little bit of how we're going to do this. Every time we go through and take notes before we do practice problems in your textbook, I'm going to do what's called a page walkthrough. So a page walkthrough is where I am going to finger walk my way through the pages of the textbook and talk about what's important there. I'm going to do this for a couple reasons. Number one, I want you to learn the physics. It's fun. It's good puzzles to solve. Number two, as you get into higher grade levels, we're going to be asking you to do quite a lot of reading through a textbook. Textbooks can be really boring and terrible. Sorry. So I want to give you some skills to be able to look through the textbook, find the important stuff so that you can get all of the learning out of it while you're reading. So I'm going to try to go really quick through the textbook, highlight some really important information, and then jot it down as you take notes. So I am going to pull up my notes document, and I'm going to talk through what we are seeing here. Let's see. All right. So here is my notes document. Let's get started. So on your textbook, we are going to start on page 103, and we're going to open up and start looking at work. Before we get started, let's title our page. I believe this should be page number 7 in your notebook. As always, if you have a slightly different page count, that is fine. But I am on page 7 in my notebook, so you might be somewhere close. Maybe it's 8, I don't know. Somewhere there. And this is going to be a walkthrough about the topic of energy, looking at chapter 8. Specific topics that we'll be talking about are work, power, energy, mechanical advantage, and efficiency. This is effectively all of the second page of your physics everything sheet. So you've already got a lot of this information on your physics everything sheet, but now we're going to talk about it a little bit more in depth and do some examples. All right. So starting on page 103, it introduces the topic of work. And it has a bold word, work, which indicates that it's probably pretty important. It's also the title of the section. So I'd say work is definitely worth noting. So I am going to start by writing down the main topic, which is work. If I flip onto page 104, it gives me some italics, and the italics has the equation for work. And work is equal to force times distance, W equals FD. All right, so that stands for work is equal to force times distance. What that means is that work is the amount of force that I'm exerting over a certain amount of distance. Remember, you have to actually put a force on something and the thing has to move somewhere. So you need both the distance and the force. In terms of details that we already know about work, work is using the unit joule, Joule. Remember, a joule is equal to a Newton times a meter. And a Newton times a meter, since a Newton is a kilogram meter per second squared times a meter, you could also say it's kilograms meters times meters over second squared, which is equivalent to kilograms meters squared over second squared. So all of these units are the same thing. We're always going to convert them down to the simplest version, which is joule. Joule is our nice simple version because it's much easier to say than kilograms meters squared per second squared. Okay. In the picture in figure 8.1, there is this weightlifter, and it asks, If the barbell could be lifted twice as high, the weightlifter would have to do twice as much work. I guess that's not really asking, that's telling. So I like looking at the captions and the pictures when I'm going through the textbook. So far I'm looking at the equations, I'm looking at the bold words, I'm looking at the titles, and I'm looking at the pictures and the diagrams and the captions on them. So what that tells me is that this is a proportional relationship, a directly proportional relationship. If I go 2 times the distance, that would be 2 times the work. So those two things are directly proportional. Remember, that means when one goes up, the other goes up the same amount, the same number of times bigger. Right? So if I move something twice as far, that does twice the work. Good. Okay, the next section, 8.2, is called power. So power is the next piece that I'm going to highlight right there. And I look through and I also see this equation, power equals work done divided by the time interval. So power, P, equals the work done divided by the time interval. I'll add in little reminders that that's work and time, but you should be good for those. It says that the power is using the unit watts, W-A-T-T. And since I know that work is in a unit of joules and time is in a unit of seconds, joules divided by seconds is equal to a watt. And I know that a joule is a kilograms meters squared per second squared over another seconds. So that would be kilograms meters squared over seconds cubed, because now I have see right here, I have 2 seconds on the bottom divided by another second on the bottom gives me 3 seconds on the bottom, or seconds cubed. All right. The big idea with power is that sometimes all you care about is how much work you're doing, how much energy you're putting out, and sometimes it really matters how fast you do it. For example, when you're exercising, there are some times where if you walk 2 miles or you run at a sprint for 2 miles, you've done the same work. You've moved your body, the force, over the same amount of distance. So that's the same amount of work. But one clearly requires more power. If you're sprinting, you have to push that body much harder because you're doing more work in less time, or the same amount of work, excuse me, the same amount of work in less time. So that increases your power output. Sprinting is more powerful than walking. So if you just want to burn the same number of calories, walking 2 miles versus sprinting 2 miles should be about the same. But if you want to build strength and get more powerful, the sprinting will help you build a little bit more leg strength. All right. Then at section 8.3, it starts talking about mechanical energy. I'm on page 105 now. You go ahead and flip pages with me. So mechanical energy, there are a few different types. We're going to talk about 2 types of mechanical energy, potential energy and kinetic energy. So the first one in section 8.4 on page 106 is the potential energy is the energy that you have at a height. We've already got this in our physics everything sheet, so I'm going to go reasonably quick here. There's a nice diagram on page 107 that shows that there are 3 different heights, or sorry, 3 different diagrams. Each one involves the same boulder moving up the same 2-meter distance. So since I have the same height, I have the same mass of the boulder, I have the same gravitational acceleration because we're all on the Earth, all 3 of these are equal to each other. So that is equal to that is equal to that. It doesn't matter which pathway I take, whether I go straight up, or whether I go up on a ramp, or whether I go up in little steps. Each one has the same end result. So they all 3 have the same change of potential energy. And in this case, all 3, their potential energy change is 200 joules. okay, because they have the same work done, the same height times the same force of the boulder, the same weight of the boulder. It is the same potential energy. All right, we have an equation for potential energy that gravitational potential energy is equal to mass times the acceleration due to gravity times the height. So the mass of the object times the acceleration due to gravity, 9.8 meters per second squared, times how high were you able to raise it. Whoops, sorry. And this note down here is that up here in A, B, and C, all three have the same potential energy, regardless of what their path is. On page 108, we talk a little bit about kinetic energy. So kinetic energy is the energy due to movement, and the equation for that is 1/2 times the mass times the velocity squared. In figure 8.5, right here, there are pictures of 3 cars going at different speeds, and then it shows how long it takes to stop. Because kinetic energy is based off of velocity squared, the faster you're going, you can square that and find how much more energy you have. So in this case, if I'm going 30 kilometers per hour, it takes me 10 meters to skid to a halt, right? I apply the brakes, I have a set amount of energy. Now, if I double 30, that means I've gone times 2 right here, from 30 to 60. My 10 meters goes to 40 meters of skidding because my velocity is squared, right? So 2 squared gives me times 4, right? 4 times more kinetic energy. So it takes me 4 times longer to skid to a halt. I go from 10 to 40. That's a times 4 ratio. Then if I double it again, times 2 again, I go from 60 kilometers per hour to 120 kilometers per hour, and I square that, right? So that's velocity squared. That would again go times 4 more. So 40 meter skidding distance goes to 160 meter skidding distance. So this is why when you're learning how to drive and your parents tell you to drive slowly, it's really, really important. The faster your speed, the more distance it takes to stop, and not just linear more, but squared more. So if you're carrying a squared amount more energy, going from 30 kilometers per hour to 120 kilometers per hour, that's times 16, because it's squared twice. 16 times more energy becomes much, much more dangerous. So drive slow, drive safe. Physics tells you to. All right. Conservation of energy. So over here, we're going to talk conservation of energy. So conservation of energy is the idea that energy is not lost or gained, it is transferred. Energy is neither created nor destroyed, but transferred from one form to the other form. This was like our pencil picking up, dropping thing. The amount of work is equal to the change of potential energy is equal to the change in kinetic energy. And I can show that in a few ways. One nice way of showing it, and this is on page 110, flipping the page, is I could show it with this pendulum. So the pendulum right here is moving back and forth, and I go from, when the pendulum is at its, the way a pendulum works, it swings like this. It's like a swing. So when it's on the far outside edge over here, it is all potential energy. It goes back, and then it stops, and it sits still right here, right before it comes back forwards again. So for that moment where it's just sitting there on the outside, it's all potential energy. When it's in the process of swinging, when it's halfway there, it has some energy where it's still a little bit high, but it's also moving, so it has some kinetic energy. So it has some potential and some kinetic. When it reaches the very bottom of the pendulum, straight vertical, it is now as low as it can get because the string's holding it up. So it has no more potential energy left. It's all kinetic energy. So they've made this big kinetic energy. And then it swings the other way out the far end and turns back into all potential energy. So a pendulum is just a transfer mechanism from potential to kinetic to potential to kinetic to potential to kinetic. Just keeps going zoop, 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 zoop. And it goes fastest at the very bottom. And then it comes to a stop at the very top before it switches directions and goes the other way. Another way of kind of looking at that with numbers now is let's take a look at this lady jumping out of a burning building. And she is going to fall out of the burning building down into the firefighter's net. Good job, firefighters. That's a very old school way of catching somebody. So she's going to start with a potential energy of 10,000 joules up at the top, up here. And as she falls, some of her potential is going to transfer to kinetic. So half or a quarter of the way down, she still has 3/4, 7,500 joules of potential, and 1/4, 2,500 of kinetic. When she's halfway down, it's 50-50, half potential, half kinetic. When she's 3/4 of the way down, it's a quarter potential, 3/4 kinetic. And when she's all the way down at the bottom and the firefighters catch her, she is all kinetic energy and no potential energy. So it's just transferring in a linear scale this time from potential directly to kinetic. The further lower you go, the less potential you have, and thus the more kinetic energy you've picked up. All right. So let's talk a little bit about machines. So one of the big things we're going to do for your Rube Goldberg project is some simple machines. So one of the machines that we're going to take a look at is a lever. And a lever is a really nice one. You can use it like a seesaw because it balances. And so it's really easy to see whether things are in equilibrium, whether they're balanced, or whether they're out of equilibrium and unbalanced. On a seesaw, on a lever, if it is up in the air and it's sitting straight, it is balanced and equilibrium. And that means both sides have to be equal to each other. So out here, we've got our seesaw sitting like this. It has a fulcrum somewhere in the middle. It doesn't have to be perfectly in the middle, but somewhere in the middle, there's a fulcrum here. This part right here is called the fulcrum, where it sits. And I know in order to stay balanced, I need the energy on one side, right? Energy on side one has to be equal to the energy on side two. So what that means is the work, which is a type of energy, on side one has to equal the work on side two, or the force on side one times the distance of side one has to equal the force on side two times the distance on side two. And I can measure these forces and distances in a few ways. I could say, okay, this is my force on side one. And then over here, this is my force on side two. And then for distances, I could measure the distance from here to the fulcrum. That's the length, which is a distance for side one. And I could measure the distance from here out to side two. And that would be the distance for side two. So the force times the distance on this side, the one side, has to be equal to the force times the distance on the other side. I could also represent it in this way, where maybe my seesaw or my lever is imbalanced, so that I have a very short side over on one end. So this side is much shorter. As a result, that side doesn't go up as much. So it has a small distance, little d, but it exerts a big force, so a really big F. As opposed to the other side, where there's a long distance, that means vertically it's going to rise a long way with a smaller force. So if I push down less on this side, I'll be able to exert more force on this side. They're representing that with the size of the letters. Small force, big distance, is equal to a big force times a small distance, because that has to equal that. The two sides are equivalent. Awesome. Let's keep on pushing through to page 114 and 115. And on page 114, 115, we introduce the idea of mechanical advantage. So mechanical advantage is how much easier a task makes something. For ideal mechanical advantage, we are assuming that there is no friction. So if I'm just measuring the ratio of the distances, that's assuming no friction. The bad news is that everywhere on the Earth, there is friction. So ideal mechanical advantage only happens in one place and is a fictional place. And it's a place that I'm going to call Magic Happy Physics Land. In Magic Happy Physics Land, there is no friction. There is no air resistance. All the molecules just move smoothly past each other with no interference at all. So we're going to do a lot of our textbook work in Magic Happy Physics Land because it makes calculating things a lot easier. And then when we do our engineering work, you're going to start realizing that friction is kind of a big deal, and it makes things much more complex. So we get to do both. We get to spend some time in Magic Happy Physics Land in our physics textbook, and then we get to see in the real world that life is much more complex and a little bit tougher. So we get the real practical engineering part. Just be forewarned that we can calculate an ideal mechanical advantage, and then our real mechanical advantage that includes friction will be slightly different because of that. All right. Last piece, I believe, is efficiency. So efficiency is how much work is useful out of the total work. So I've done a certain amount of work. How much of the work went where I wanted it to go out of the total amount of energy that I put in? For example, if I said my body is a machine that is designed for just running, right? Well, I eat 2,000 calories a day, right? That's an amount of energy that I put in. How much of that energy actually goes to moving my body forwards in running? Probably not that much. Maybe 500 calories, maybe 1,000 if I go for a big run. But that's like 25 to 50% efficient. Turns out my body is not built perfectly for running. My body wastes, quote unquote, wastes all this energy on things like heartbeat and breathing and maintaining a temperature of 98.6 degrees Fahrenheit. Now that's not actually wasted, that's keeping me alive, which is what my body's really doing. But it uses a lot of energy for heat, right? For all of those other physical functions that aren't muscle contraction for running. So efficiency is how much work is going to what I say is useful out of the total. And that's easier to calculate in something like a car that has a really obvious function, which is moving things forward. So in a car, I could take a look at the fuel energy going in. Now that would be like 100% of the energy is how much fuel is going in. And then I could look at how much goes to other places. So cooling water, just to keep the engine not overheating, takes up about 35% of my energy. The engine output, so that's the actual engine running, moving the car forward, gives me about 30% of the energy. And then exhaust heat is about 35%. So in this example of a car, how much is actually efficient? Only 30%. 30% is going to moving the car forwards to the engine's output. And then the other 70% is going to heat. It's heating up water and it's heating up the exhaust. So it's only a 30% actual efficiency. And most machines will be that way. Let's see, flipping on to page 117, that was the car. The last piece is I can find efficiency by taking a look at the actual mechanical advantage, including friction, divided by the ideal mechanical advantage, which doesn't include friction. All right, so now we are going to do some practice problems. The practice problems you're going to do are in Chapter 8. For Chapter 8, that's on page 119 through 121. All right, so this is page 119 through 121 of your textbook. And for the first set, I would like you to restate the question in your answer. So that's for numbers 2 through 4, 7, 8, 10, 16, and 18 through 20. And I've underlined those in red. And then for numbers 22, 24, 25, and 27 through 30, please write out the needs and givens and solve them like a word problem. All right, good luck. And I will post a key for Chapter 8 as soon as they are due, which I believe will be on Friday. Have a great time working on your Chapter 8 practice problems. All right, have a good one, guys.